Greetings, everybody. Hope everybody's doing well. Today, I want to talk to you guys about bases. So, the last few days, we worked through all the different things that we wanted to learn about acids. And you've already learned a lot about bases. You just didn't know it at the time. So the first thing we did with acids, we went through our properties, and then we went through the types of acids. And we said that there were three. The Arrhenius model creates the H3O plus, the hydronium ion. The Bronsted-Lowry model is a proton donor, right? The substance, right, that gives or loses an H. So HCl becomes just Cl. It lost an H. And we focused on the donor when we were going through that. But I'm sure some of you noticed, well, if the HCl is losing an H, the water is gaining an H. And that will be, you find, what the definitions of some bases are. Right, so your Bronsted acids are proton donors. Your Lewis acids are electron pair acceptors. And then we talked about how do acids break down? Why is it some are able to conduct electricity? And that got us into strength of acids. And we found out we have strong acids and that we have weak acids. All right. And your strong acids are the ones on this list of 6. And any other substance that starts with hydrogen and isn't on the list of 6 is a weak acid. And your strong acids break down 100%. And weak acids break down roughly 5. And if you want to learn more about weak acids, take me next year. It's actually incredibly more complex than that. But for our purposes, weak acids break down roughly 5%. And then I had some pictures to help you see that, right? Your strong acid, before it breaks down, the red bar, entirely HA. After it breaks down, there is no HA, no red bar left. It's all purple and blue. And the weak acid, on the other hand, is less than 5%. So we start with HA, and at the end of the dissociation, notice we still have a very large bar of HA present and tiny amounts of H plus and A negative. And then we had a conversation about the difference between strong and concentrated or dangerous. And we tried to debunk any myths that just because an acid is termed strong, it's somehow scary, it's somehow dangerous to me. And the take-home message there was strong and weak have to do with the list of 6 and 100% breakdown or 5% breakdown. Concentrated and dilute have to do with danger and the molarity of the substance. The more acid that's dissolved, the more dangerous it becomes, the larger the molarity. So dangerous things tend to be concentrated things, and dilute things tend to be safer things. And then I said, hey, there are some acids that can donate more than 1 proton. They're called polyprotic. And we said if it donates 1, it's called monoprotic, 2 is diprotic, and 3 is triprotic. And anything more than that, or the whole thing in general, is known as polyprotism. Right, so there's the first side of the coin, so to speak, with acids. So the other side of the coin is the bases, but things should feel much more familiar because I'm just going to be talking about the opposites of a lot of things. Right? Just like we started with acids, let's start with some properties of bases. Right? Bases, right, have a taste. It's bitter. Right? Almonds are said to be bitter tasting. Soap, if you've ever got soap or shampoo in your mouth, they say that tends to be bitter. So acids are sour and bases are bitter. Right? Bases change the color of indicator blue. Right? So acids turn indicators red. So if I take blue litmus paper and I put it into a base, it stays blue. If I take red litmus paper and I put it into an acid, it turns blue. And generally, if I put in pH paper, which tells me a number system, right, pH, right, the higher the number for the pH, the more blue shade the pH paper tends to become. A third characteristic of bases is they tend to feel slippery because they have a tendency to react with the oils in your skin. So if ever you're in my chem lab and your hands start feeling very oily or very slippery, you should stop and wash your hands because you probably have some base on your hands and it's breaking down the oils in your skin. 4 is the total reverse. On the earlier slide, it said acids react with bases to make salt and water. Well, the reverse has to be true then. Bases react with acid to produce salt and water. And lastly, bases can conduct an electric current just like acids do, depending on whether they are strong or weak. All right, so I can sum up the types of bases much faster than the acids because you know what to look for. All right, so the Arrhenius model is the one that's looking for a specific ion. All right, the ion it's looking for, right, in an acid is the H3O plus ion, hydronium. The ion they're looking for in a base is the hydroxide ion, which is OH negative. So if you see an equation written and there is OH negative on the right side, wherever it came from, that substance is going to be an Arrhenius base. My Bronsted-Lowry model, Bronsted acids are proton donors, which means the reverse is a Bronsted base. So if I am a proton acceptor, I am a Bronsted base. And then lastly, my Lewis base is an electron pair donor because a Lewis acid is an electron pair acceptor. All right, so if we go through the Bronsted base, which is, again, the most common, the most useful, if I look at this equation, and this picture here just shows you how it occurs, you would know everything you need to know from looking at this equation. First thing you do is you spot the things that look similar on each side. All right, so what looks the most like HCl? It's the Cl. What looks the most like H2O? H3O. And that lets you know what happens with the proton. All right, so HCl becomes Cl, which means it lost an H. Right? So that's my proton donor. So HCl is my acid. Right? Then I look at the other substance. All right, what's H2O? Oh, H2O becomes H3O. Right? How do I go from H2 to H3? Oh, I gain an H. I accept an H, which is why H2O is my Bronsted base. It is accepting a proton. Here's another example, right? If we look at H2O and NH3 going to NH4 and OH, right? We look, okay, who's H2O's partner? It looks like OH negative. Who's NH3's partner? Looks like NH4. All right, so we spot, right? So H2O becomes OH, which would be H1O. All right, so there's my proton donor, so no good. NH3 becomes NH4. I have one more H. There is my proton acceptor. So NH3 is my Bronsted base. And if you look over here, sure enough, we see the hydroxide ion on the right side. That means that NH3 is also an Arrhenius base. All right, so even though the NH3 doesn't possess OH in it, so long as it creates it as a product, it will fit the definition of an Arrhenius base. And remember, if you are a Bronsted, you are automatically a Lewis, which is why we don't dive into this as much. Right, the NH3 has to be your electron pair donor to become NH4. So as soon as you know it's a Bronsted, you can go right ahead and say, I know that substance is a Lewis. And we'll do a lot of that at the beginning of next week when we go through identifying acids and bases. So we talked about how acids break down, dissociation. We're going to do the same for bases. So if I'm looking at the dissociation of a strong base, just like acids, they break down 100%. The acids have a list of 6. The bases have a list as well, all right, but it's not the same list of 6. All right, so your list of strong bases are metallic hydroxides. All right, so group 1 hydroxides, right, are all strong bases, and there are 3 from group 2 that are strong bases. All right, so if I made a list of 6 that you guys could copy down on this slide, all right, or note down, all right, so that way you'd have a list of 6 for both. All right, my strong bases are any of the group 1 hydroxides. So we're looking at LiOH, we're looking at KOH, we're looking at RBOH, we're looking at NaOH, right? And if I were to show you it on a periodic table, I'm just working my way down the group. So LiOH, NaOH, KOH, RBOH, we'd have CSOH, we'd have FROH. Right, so those are all my group 1 hydroxides. And then, like I said, there are 3 from group 2. Right, Ca, when it's with OH, right, it's CaOH2. You've got Sr, OH2, and you've got Ba, OH2. All right, so this is my list of my strong bases. All right, and these guys are your base list, just like acids. They break up 100%. They conduct really well. Any other substance that we have identified as a base, a proton, acceptor, or something that creates OH, those will be weak bases. So if you're not on our list, you would be deemed a weak base. You would break down 5%. You would conduct just a little bit. All right, so you've got strong acids, strong bases, both 100%, both conduct really well. Weak acids, weak bases, they're not on the lists. They break down 5%. They conduct a little bit. All right, and while we're talking about identifying acids and bases, you're going to notice that certain substances, based on their structure, they can give an H or they can receive an H. And depending on who they're mixed with, they will do both at times. They favor one over the other, but sometimes they possess the ability. So if we look at NH3 in this top equation, NH3s with H2O, we get NH4 and OH negative. NH3 becomes NH4. How does it do that? It gains an H, right? If I'm a proton acceptor, that makes the NH3 a Bronsted base. So it's a Bronsted base. Notice, same reactants, NH3 and H2O, but this time we made different products. We made H3O plus and NH2. So if I look here, NH3 is partnered with NH2. How does it go from NH3 to NH2? It loses an H. In this setup, it would be a proton donor. So notice NH3 plus H2O, NH3 plus H2O. In one instance, it's gaining an H. It's an acid. In one instance, it's losing an H. It's gaining an H. It's a base. In one instance, it's losing an H. It's an acid. That is known as being amphoteric or amphoterism. Right? You have the ability to act as an acid or a base. So understand, to be amphoteric, you have to have hydrogen in your formula, right? So no substance that doesn't have hydrogen in its formula could be amphoteric. Right? And if you're paying attention, water is also amphoteric in this setup because look, in the bottom one, H2O becomes H3O. It gains a proton. That makes it a base. In the top one, H2O becomes H1O. It loses a proton. It's an acid. So there were 2 amphoteric substances in that setup. All right, and that sets us up for talking about the stuff on the other side, which will be on Monday, where we talk about conjugate acids and conjugate bases. All right, and we'll do that. I'll get you guys some practice at identifying those. And then Wednesday will be all about identifying acids and bases. And then Thursday and Friday, we'll wrap up anything we haven't covered yet. And I'll give you guys time to chip through just a short acid base exam to kind of wrap up the school year. All right, so all you guys have going right now is your test for over the weekend. Make sure you get that to me by Sunday. I will jump onto the Google Meet at 1 o'clock. If anybody's really struggling or has any questions about the setup of the exam, right? Remember the multiple choice, right? You have to have justifications for. Right? So if you're looking at the test itself, right, I should see justifications for numbers 1 through 35, all right, are my justifications. And the ones that go with the graph, if you're pulling it from the graph, it's okay to say that, right? Right? So if you're saying, oh, okay, what's going on? All right, I'm landing at these conditions, you know, what substance or something like that, you could say, oh, I got that number from the graph, right? But if you're trying to say, oh, what type of solution is it? Remember, if you're above the graph, you'd say it's supersaturated. And you would want to say, oh, because I'm above the curve, it's supersaturated. Because I'm under the curve, it's unsaturated. That's what justifications for the graph look like. You do not need to justify, all right, these fill in the blanks. Right, the 36 to 40 or the 41 to 55. I don't need justifications for those. All right. And notice you are supposed to answer all 3 essays. All right, this time. All right. So like I said, if you have any questions with the test, please feel free to reach out. Other than that, I hope everybody is doing well. And I look forward to seeing you guys soon. All right. Thanks for checking in.